भवतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै।
In the last lecture, you were introduced to the concept of Z transform of a discrete time system, and we also saw the Z transforms of some basic discrete time functions. Let us recall what we did. Given a sequence of values Fn, we said that the Z transform of that f of z is given by Fn z power minus n going from 0 to infinity, and this being the one-sided Z transform of the discrete time signal f of n. What this means really is that the kth sample, which is fk, is given a weight z to the power of minus k. So fk is made fk multiplied by z power minus k, and the summation of all such terms gives you the f of z. Conversely, if I have fk minus zk alone standing by itself, that is the Z transform of a single value f of k standing at the kth instant. That means delta n minus k fk has a Z transform fk z minus k, or delta n minus k has a Z transform z minus k, where k is a constant. We also saw that this kind of transformation, this whole series Fn z power minus n, converges for values of z greater than a certain constant r, where r defines the region of convergence. So if this is the radius r, so this is the region of convergence, which we abbreviated as ROC. Region of convergence is indicated as ROC. That means the region of convergence is the region outside a circle of radius r, where the value of r depends upon the particular function f of n. We have seen that in a few special cases, for example un has the Z transform z upon z minus 1, and the region of convergence for this is z greater than 1. If you see the Z transform of un, it has got a 0 at the origin and a pole at 1. So the region of convergence is 1 outside this pole. So it turns out that the region of convergence is the region outside a circle. That circle must include all the poles of the particular Z transform. Similarly, if you take cos omega n un, you find that the Z transform of that is z times z minus cos alpha divided by z squared minus 2z cos alpha plus 1. Now if you look at the poles and zeros of this particular function, it will be like this. There is a 0 at the origin, z times z minus cos alpha. There is a pole at, there is a 0 at cos alpha, and this denominator gives rise to two factors which give the poles at these 2 points. So So this angle being, I'm sorry, this is cos omega. It should be, this is cos omega n omega, therefore this should be cos omega. This will be cos omega, this should be cos omega plus 1. So the angle of this is omega, so this is e to the power of j omega, this is e to the power of minus j omega. So these are the poles. Again, the region of convergence is outside the poles. That means the pole which is the outermost pole, the pole which is at the largest distance from the origin, defines the value of r, and therefore the region of convergence is such that it does not include any one pole of the given Z transform. So this is how it goes. Now we were also discussing the properties of the Z transforms, and we mentioned the first property is the linearity, which we already discussed. The second property we mentioned was delay in time. So let us take first of all a causal signal. So if f of n un has the Z transform f of z, we said then if this function is delayed by m units, f n minus m un minus m has the Z transform z power minus m f of z. Why it happens is because if you have fn un, you have samples like this. Fn minus m un minus m will have the same sequence of samples but delayed by m units. So this is 0, this will be m. So what it means is if there is a particular sample fk, it is given a weight z minus k in forming f of z. Now the same fk will come m instants later, therefore it is given a weight of z power minus k minus m. So every sample here which was multiplied earlier by a certain power of z, now it is multiplied by a certain power of z plus multiplied by z minus m further. Therefore the whole series now will now be multiplied by z power m, and in the process when you delay this, no new samples are introduced because this is a causal function. Therefore earlier we assumed these are zeros for negative values of n. So when you delay this function, these zeros, these non-zero values will occur here. Therefore no new samples are introduced as a result of this shift. So consequently a causal function, if it is delayed by m units, you have the Z transform z power minus m f of z. What happens if f of n has some values for negative values of n? So a non-causal function. So let us take this. You have f of n, you also have some values, let us say. Then it is delayed by m units, therefore f of n minus m, this original value f0 gets shifted here and you have these values, but these also come, this whatever are occurring at negative instance of n will also appear here. So this is, so when you are forming the Z transform of this, you not only take into account the values of this set of samples, but also you have new samples introduced here which were not present in forming f of z from f of n. By the arguments that we have already advanced in the case of causal signals, if this Z transform of f of z, this set of samples multiplied by the appropriate power of z will certainly give z power minus m f of z. But in addition you have these samples. They must also be given attention to in forming the Z transform of f n minus m. So let us see what these samples, what are the additional contributions of these samples. The sample that is coming here was originally at minus m. So this will be f of minus m. F of minus m is now standing at the origin. So when you are taking the Z transform of that, you have f of minus m multiplied z power minus 0, which is of course 1, and this sample is f of minus m plus 1, and that will have a weightage z minus 1 because it is occupying now the position 1 in the series. Like that it goes on, and the last sample that is newly introduced is f minus 1, and that of course has a power of z power minus m minus 1. So when you have a non-causal signal, the new Z transform will now include not only this quantity plus also the additional quantities here. So that means we can say if f of n has the Z transform f of z, then f of n minus m will have the Z transform f of z z power minus m plus f of minus m plus f of minus m plus 1 z power minus n, like that, f of minus 1 z power minus m plus 1, that's last one, minus m plus 1. So this is important because sometimes when you take difference equations, you are prescribed certain variables which are initial conditions are prescribed at minus 1, minus 2 and so on and so forth. That means one of the variables is said to have values at negative values of n, and therefore when you delay it, suppose yn is said to have given values at minus 1 and minus 2, when you form yn minus 1, yn minus 2, you are delaying that. Those values come into prominence here in yn minus 1, yn minus 2, and you must take their values into account in forming the appropriate Z transforms. So this is important that you should keep this in mind. For non-causal signals, it is of course straight multiplication by Z power minus m. For causal signals, for non-causal signals, you must take these values of the samples also into account. Now let us consider what happens if the signal is advanced. Instead of delay, we advance the signal. So if I have Fn like this, if you advance it, it will be like this. So what was f0 here occurs at this point at an instant m. This is f of n plus m. So if it is advanced by m sampling instants, the sample occurring at 0, n equals 0, now occurs at n equals minus m. So the Z transform of that is f of z, where a kth sample here, f of k, has been multiplied by z minus k in forming this. Now the kth sample here, the f of k occurs at not at k but k minus m. Consequently, the contribution of fk in this Z transform of this advanced signal would be f of k z of minus k minus m, or f of k z power minus k multiplied by z power m. So if this is f of z, one would expect that the Z transform of that would be f of z times z power m. But we must take into account the fact that when we are forming the Z transform of this, we take into account only these signals. All the signals are ignored. But in this expression, the contributions due to these samples also are introduced. Therefore, from this expression, we must subtract the contributions of these samples which are ignored in forming the Z transform of f of n plus m. So f0 would have contributed z power m, because after all f0 was standing by itself f0, but when you are multiplying by z power m, f0 times z power m would have been the contribution to this. So you must have minus f0 z power m. The next sample, which would have been fn, f1, in this f of z it would have multiplied by z power minus m minus 1, but you are multiplying by z power m, therefore z power m minus 1 is the contribution to f1. Like that it goes on. The last contribution was due to this. This is now fm, and this sample is f of m minus 1. So f of m minus 1, in forming this z transform, you would have multiplied by z power 1. So this then is the resultant z transform of an advanced signal, f of z times z power m minus the contributions of all these quantities, which have been ignored in forming this. So this is to be taken into account because after all you are forming the z transform on a single sided basis. Therefore all the samples which are occurring at negative values of the independent variable are being ignored, and therefore you must make a suitable correction for this. In a two-sided z transform, the samples extending from minus infinity to plus infinity are considered. Therefore this additional correction will not be there in a two-sided z transform, but we are discussing only a single-sided z transform. Therefore this correction is necessary whenever a signal is advanced. Let us consider a few examples. Suppose you have a sample of value 1 at n equals 2 and 0 everywhere else. Now this is obviously delta n minus 2. A unit impulse, if this sample was standing here, you would have said it's delta n, but it is delayed by 2 units, delta n minus 2. Since we know delta n has a z transform 1, delta n minus 2 must have a z transform z power minus 2 times 1, and that is all, that is the z transform of this. Similarly, suppose you have a function which is like this, 0 everywhere for n less than 1, and for n 1 and beyond it is equal to 1. So this is also 0. This is obviously u of n minus 1, a unit step starting at n equals 1. Since un has the z transform z upon z minus 1, un minus 1 is z upon z minus 1 multiplied by z minus 1. Therefore this is 1 over z minus 1. That is the z transform of this. Let us take a third example. Suppose Fn consists of unit samples from 0 to say m. Now this can be written as unit samples right through minus a function which has minus 1 value from, say, this, suppose this is, you want up to m, therefore this is, if you take m plus 1 onwards, this has minus 1 value. So if you add these two functions, then you get this. So up to m the value is 1, and beyond that it is 0. Therefore you can write this is u of m, this is u of m, this is u of minus, because it's a negative sample, this is a minus, it's a negative sign here, all the samples have negative value, but this step function starts at m plus 1, u of n minus m plus 1, that is what it is, u of n minus m plus 1. The z transform of this is z upon z minus 1 minus of the z transform of this function. The z transform of this function is the same step function which is delayed by m minus 1 seconds. Therefore, z upon z minus 1 multiplied by z of minus of m plus 1. So it is delayed by m plus 1 units. Therefore, that is its z transform. Therefore, we can write this as z upon z minus 1 times 1 minus z power minus m minus 1. Fourth example. Suppose we have a discrete time function which goes like this. Like this. So up to mth sampling instance it raises uniformly up to the value m, and thereafterwards it remains constant. So this is your discrete time function as a function of m. Now, to find the z transform of this, we can regard this as the sum of a ramp function, unit ramp function, which continuously rises, and then at the mth sampling instant here, after all, up to 0 to m, the ramp function answers the given function of time. But beyond that, this growth should be arrested. So whatever you are having here must be nullified, the increase must be nullified. So if you introduce a negative going ramp here, such that the negative going ramp has negative values, so that whatever increment is caused here is cancelled by this, that means this portion and this portion gets cancelled out, then what is left here is the growing function up to this point, and beyond that it retains its value, which is equal to m. This is of course m. Consequently, the given function can be thought of as the sum of, after all this is R of m, the ramp function. And what is this? It is also a ramp, but with a negative slope. Therefore minus, you must have a negative out in front, but this ramp is now delayed. It starts at not at 0 but n equals m. Therefore this is minus of R of n minus m. So in other words, the given function of time, discrete function time, is Rn minus R of n minus m. So consequently, its z transform would be z upon z minus 1 whole squared minus of the z transform of this is z upon z minus 1 whole squared, but it is delayed by m sampling instance, so it must be multiplied by z power minus m. So that is the z transform of the second ramp. So this can be put, of course, z upon z minus 1 whole squared into 1 minus z power minus m. That is how one can observe, we can use the rule for the z transforms of delayed time functions to find out the z transforms of discrete time functions of the type that is sketched here. Let us now consider the next property, multiplication by m. If Fn has the z transform f of z, then Mfn has the z transform minus z df by dz. This is the result. Proof. Let us consider f of z. This is after all Fn z power minus n. Let us take the derivative of this dfz over dz, assuming that when you want to take the derivative of the series, you can take the derivative under the summation sign. This will be f of n minus n z power minus n minus 1. So consequently, if I multiply this by minus z dfz by dz equals, this minus sign cancels with this minus sign, and you have Nfn, and since you are multiplying by z, this becomes z minus n. and this is after all the Z transform of NFN. So the definition of the Z transform of NFN is this. So NFN times Z power minus n is what we are having here. Therefore, Z transform of NFN is this quantity, and that is what we have got. And this is the property 4, which we have just now derived, property number 4. Let us work out a couple of examples illustrating this property. We know that Un has the Z transform Z upon Z minus 1. Now, what is the Z transform of NUN, which is of course Rn? We can find this out, deduce it from the Z transform of Un by using just the property that we have just now discussed. This is minus Z d by dz of Z upon Z minus 1. So that will be equal to minus Z times Z minus 1 times the derivative of this minus Z times the derivative of this divided by Z minus 1 whole squared. Therefore, this will be Z upon Z minus 1 whole squared, a result that we already know. Now, suppose I want to find out the Z transform of n squared Un. That means this particular function is multiplied by n again. Therefore, its Z transform is minus Z d by dz of this expression, Z upon Z minus 1 whole square. You can carry this out and show that the result equals is Z times Z plus 1 over Z minus 1 whole cubed. So that's how it goes. You don't have to remember this particular Z transform. You can always derive it from the Z transform of NUN. Let us now consider the next property. Complex scale change. If Fn has the Z transform Fz, then W minus n Fn has the Z transform Fwz. That means instead of Z you have Fwz. That means it's like a scaling in the complex domain, in the Z domain. Instead of Z you have Fwz. This result is quite straightforward. You can write down the Z transform from that and deduce this without any difficulty. So we will not try to construct the proof. This is quite evident. But we would like to work out an example. Example. Suppose we have cos n omega Un. We know that its Z transform is Z times Z minus cos omega divided by Z squared minus 2 Z cos omega plus 1. This is an important transform which you should keep in mind. You should remember this. Now, suppose instead of a sinusoidal function of discrete variable n as we have here, suppose we have a damped sinusoid. Suppose I take e power minus n alpha cos n omega Un. So, the Z transform of this, since you know the Z transform of this, you are multiplying by e power minus n alpha. This, if you recall the property that we have now just now discussed, this W corresponds to e power minus alpha here. So if you know the Z transform of Fn, you can find out the Z transform of W power minus n Fn. So all we have to do is replace Z by Z times e power alpha. So you have the Z transform of this Z e power alpha times Z e power alpha minus cos omega divided by Z squared e power 2 alpha minus 2Z e power alpha cos omega plus 1. This can be put in an alternative fashion which is often found convenient. Z times Z minus e power minus alpha cos omega divided by z squared minus 2z e power minus alpha cos omega plus e power minus 2 alpha. So this is an alternative expression which is often found convenient. So a damped cosine function will have a z transform like this. We can extend this to e power minus n alpha sin n omega in a similar fashion. Once we know the z transform of sin n omega, we can find out the z transform of e power minus n alpha sin n omega un. I will give the result. This will be z times e power minus alpha sin omega divided by the same denominator z squared minus 2z e power minus alpha cos omega plus e power minus 2 alpha. The point to note here is that cos n omega un has poles in the z plane at these 2 points, and this is a unit circle. At an angle plus or minus omega with the x-axis. Those are the poles of cos, the z transform of cos n omega, and the region of convergence will be outside the unit circle. Now when you take e power minus n alpha cos n omega un, the poles now will be of this is the unit circle, but the poles will be at a distance e power minus alpha from the origin and at the same angle plus or minus omega. That means the distance of the poles from the origin is not unity but e power minus alpha, which is of course less than 1. That means the region of convergence now is enlarged. This is ROC. The region of convergence there in the first one is outside the unit circle, but here outside the circle of radius e power minus alpha. That means the region of convergence has been enlarged. The reason is cos n omega is something which is amplitude is kept constant, but e power minus n alpha cos n omega is a decaying sinusoid, therefore it is decaying faster, therefore the region of convergence is also increased. That is the purport of this analysis. The next property we would like to discuss is the one relating convolution. If Fn has a z transform f of z and Gn has a z transform g of z, we would like to know what is the z transform of the convolution of Fn Gn. You recall that the convolution of two discrete time signals f and gn is defined as fn minus k gk, k from 0 to n for causal signals which we are assuming. This is also can be written as k equals 0 to n f of k g of n minus k. This can also be written in this fashion. The physical significance of this is that if you are having say this is Fn and let us say this is Gn, then what we are doing is in forming this, you take Gk and multiply each sample of Gk by Fn minus k. This is Fn. So Fn minus k would be obtained by folding this around the origin, then you would get this, and advancing this by n units. So you will have something like this. This is your f and this 0 samples here. This is f of n minus k, and this now instead of starting at 0, here it starts at n. Now you multiply each sample in Gk by the corresponding sample of Fn minus k and add up that products from n equals 0, from k equals 0 to n. That means all these samples will enter into the final, will give the final contribution. These samples are lost, these samples are lost, and therefore the summation extends from k equals 0 to n. Now the Z transform of Fn convolved with Gn is therefore equal to, by the very definition of Z transform, Z power minus n times the convolution of this. What is the convolution of that? F of n minus k gk, k from 0 to n. So this is the convolution summation of Fn star Gn, and that multiplied by Z power minus n, n from 0 to infinity. Now when k is now summed up from 0 to n, when k gets past n, Fn minus k in the argument n minus k becomes negative. Therefore, since we are assuming causal signals, Fn minus k is 0 for k greater than n. And because of this, I can write this summation Z minus n. Now the second summation, I can say k equals 0 to infinity without altering anything, because I am only adding zeros to it, because Fn minus k happens to be 0 for k greater than n. Therefore, instead of taking this upper limited summation to n, I can as well take it up to infinity. So this can be written as Fn minus k times gk. Because of this. Because of this. Now what I can do is I can interchange the summation. I will start summing up with n first and then with k. Therefore, in this double summation, I will take up the summation with reference to k later, and I will first take up the summation with reference to n. Therefore, since I am summing up with reference to n as a first step, all those which involve n will be put here, Z power minus n, Fn minus k. And all those which are not involved with n can be brought outside. They are constants as far as that summation is concerned. Now this, as you can see, is k equals 0 to infinity gk. This is, after all, the Z transform of Fn minus k. If f of n has Z transform f of z, f of n minus k delayed function will have f of z times Z power minus k. And in this summation now, f of z is a constant that can be pulled outside the summation, and all you are now having will be f of z multiplied by k equals 0 to infinity of gk z minus k. That is, after all, this is a transform of g of k. Therefore, I can write this as f of z times k equals 0 to infinity of gk z power minus k, which is indeed f of z, g of z. So the upshot of this is that Fn convolved with Gn, the convolution summation, as Z transform Fz times g of z. Convolution in time domain corresponds to multiplication in the transform domain, a result which is strikingly similar to what we had in the case, in the continuous time case, where the Laplace transform of the convolution of two time functions ft and gt is the product of the Laplace transforms. Exactly the similar result is available here also. Example, let us take as a first example un convolved with un, the convolution summation of two step functions. So to do this, we first plot uk versus k. So that is a set of discrete values, a value equal to 1 for positive k. Then you have to multiply this by un minus k. So un minus k will have, u minus k will have values for negative values of k, but un minus k you shift it by n instants. So you have like this, and beyond that up to n it is equal to 1. This is k and this is un minus k. So beyond n it is zeros, because u minus k is the same function folded on the negative direction, but you shift it forward by n instants. Therefore this is un minus k, and then you multiply these two functions. That means uk multiplied by un minus k will now be, after all this is 0 multiplied by 1, that's nothing. Therefore you have a string of ones up to, from starting from 0 and going up to 1 n, and this is equal to 1. Now in the convolution summation you take the uk multiplied by un minus k, and this means that you must add up the product values from 0, from all the product values that you got, and you have only non-zero values starting from 0 to n, and therefore there are n minus 1 such units to be picked up. Therefore this is n plus 1, and this is true for positive, for n 0 or positive, because if n is negative, for example, that means after shifting, folding uk to u minus k, if n is negative you shift it in this direction. Therefore there will be no overlap between these non-zero samples here and here. That means whatever result you got is applicable only for n greater than or equal to 0. For n less than 0, that means this sample train will now be shifted in the negative direction. Therefore the product will be identically 0. Therefore this is 0 for n less than 0. So what it means is un convolved with un, in working out in the transform in the time domain, we now observe that this is equal to n plus 1 for n greater than or equal to 0. Therefore you can write this as n un plus un, which means this is Rn plus Un. So if you find what is the Z transform of this, after all the Z transform of this would be Rn is Z upon Z minus 1 whole squared, and Un Z upon Z minus 1. Therefore the product of these, the sum of these, if you have a common denominator Z minus 1 whole squared, Z times Z minus 1, Z squared minus Z plus Z, that is Z squared upon Z minus 1 whole squared. So by working out in purely time domain, discrete time domain, you obtain the Z transform of Un convolved with Un as Z squared upon Z minus 1 whole squared. But by applying the convolution principle that we just now discussed, we can also arrive at this, the Z transform of this independently. We know the Z transform of Un is Z upon Z minus 1. The Z transform of the second Un is also Z upon Z minus 1. So the convolution in time domain is equivalent to multiplication in transform domain, and this is also equal to, therefore, Z squared upon Z minus 1 whole squared. So what we have obtained in the time domain is also the same as what we obtained using the convolution principle, which we now have just now discussed. Let us consider a second example. If a general function f of n is convolved with Un, we know its Z transform will be f of z times z upon z minus 1. Now let us look at the meaning of this convolution fn star Un. So if f of n is f of k versus is a sample train like this, Un minus k would be a negative going step starting at n and going backwards. So f of k times Un minus k will be the set of samples starting from k equals 0 to n. So the summation of this set of samples is indeed fk from k equals 0 to n, because the product will be 0 outside this range for less than n less than 0 and k less than 0 and k greater than n. So in other words, the convolution of f of n with Un is the summation of the first n plus 1 samples from 0 to n. So that means if you have f of n as the z transform f of z, the product 0 to n of f of n, f of k, that is will be equal to your f of z times z upon z minus 1. So this will be, suppose you have got a gn defined in this manner, 0 to n of f of k, that will have the z transform f of z times z upon z minus 1. This is the result which is once again similar to what we had in the continuous time system, where the convolution of unit step with a function f of t is equivalent of is integration of this f of t from 0 to t. That's something which we have already discussed. Suppose we have a periodic sequence, we have f of n which repeats itself for every n sampling instance. So in other words, f of n we said is equal to f of n plus n for all values of n. Now let us take the first n minus 1 samples which define one period. That means if f1 of n is defined to be f of n for 0 greater than n greater than or equal to 0 and less than n, that means first n minus 1 samples, and 0 for n greater than or equal to n, suppose we define that, and that will be just the samples during the first period, and everywhere else it is 0. This is f1 of n. If you know the z transform of f1 of n, you can find out the z transform of f of n because it's a repetition of the whole thing again and again. So if f1 of n has the z transform f1 of z, then f of n is obtained by having f1 of n plus f1 of n minus capital N, f1 of n minus capital 2 capital N, and so on and so forth. Therefore, this is obtained by the basic one period has the z transform. The next cycle of samples for the next period will be z minus n f1 of z plus z minus 2 f1 of z, etc., etc., etc. Therefore, this will be f1 of z divided by 1 minus z power minus n. So that is what we have. It is something very similar to what we had in the case of continuous time systems, where you have e to the power of 1 minus e to the power of minus st is what we had here. In this case, this is how it will be. This can be further written as z minus n times f1 of z divided by z minus n minus 1. The next property that we would like to consider it is the initial value theorem, which is the counterpart of what we had in the continuous time system. By definition, f of z equals f0 plus f1 z minus 1 plus f2 z minus 2, etc., etc. So if you take the limit as z tends to infinity of f of z, if you take z to a very large value and take the limit as z tends to infinity, all these terms will become insignificantly small and you get f0. So the initial value theorem states f0 is limit as z tends to infinity of f of z if such a limit exists. So this is a very simple rule, that is the initial value theorem, and we must also keep in mind that z is going to infinity, that means z equals infinity must be in the region of convergence. So if you are having a single sided z transform where this is the region of convergence, therefore z going to infinity is allowed. This may or may not be true in the case of two sided z transforms. So the z equals infinity must be in the region of convergence. Example. we have, suppose xz happens to be 2 upon 1 minus 2 power 2 times z minus 1. This is the z transform of a certain function xn. Therefore, from this you can find out x0 as limit as z goes to infinity of 2 upon 1 minus 2 power 2 times z minus 1, and as z goes to infinity this becomes 0, therefore the second term will become 0, so 2 divided by 1, that is 2, x0 equals 2. And when you are talking about z transforms, discrete time functions, there is nothing like 0 plus 0 minus, there is only values at discrete points, therefore x0 equals 2. So this is an application of the initial value theorem. We also have the final value theorem. I will just give the result and we will discuss this in the next lecture in its implications and its proof, but let me just state this property, property 8, final value theorem. The statement of the theorem goes like this: if all poles of 1 minus z power minus 1 times f of z are inside the unit circle, that is z minus 1 divided by z times f of z, this function is analytic outside and on the unit circle if this condition is fulfilled, then the final value of f of n, f infinity, which is really limit as n goes to infinity of f of n, is given by limit as z goes to 1 of 1 minus z power minus 1 f of z. So that is the statement of the final value theorem. The conditions required are that 1 minus z power minus 1 times f of z should not have any poles in the unit circle, outside the unit circle, and even on the unit circle itself. So provided all the poles of this are inside the unit circle, then the final value of f of n is given by this expression. The proof of that will be constructed in the next lecture, but we can notice that this is the counterpart of the final value theorem that we had in the continuous time situation.